Okay, so the next topic that we are going to cover is something on fuzzy sets and systems which are based on fuzzy sets. So this comes under the way that we need to handle uncertainty. So till now we have seen that we are going to handle uncertainty by using probability, things like belief networks, decision networks, etc. So one more method which can be used is the fuzzy sets. So let us see how the fuzzy sets actually work. So fuzzy logic is based on computing degree of truth. Okay, so when we consider a set, we know that a set consists of elements which are members of that set. So these elements which are members of the set, in the case of crisp logic, we say that it's either 0 or 1, true or false. Okay, so it either belongs to the set or it doesn't belong to the set. But in the case of fuzzy logic, we talk about the degree of truth. Okay, so what is the degree to which it belongs to the set? Okay, so it's a sort of many valued logic. And the truth values range between 0 and 1. Okay, and it's not just 0 and 1, or it's not a binary value. So the binary thing that is 0 or 1, true or false, is the crisp set. Okay, so in a crisp set we can say that an element either belongs to the set or it doesn't belong to the set. But here it belongs to the set with the degree of truth, or what is called its membership value. Okay, so degree of membership in the set is what you have to see, and this can be used where precise data is not available. Okay, so this was started by Zade in 1965, who was in University of California. Okay, so he felt that when the complexity is there and the complexity increases, then fuzzy logic methods are the ones which actually work basically. Okay, so let us see what you mean by a crisp set. So suppose we have the universal set X, okay, which you could say in this case is all the students in the class. And then we have the set G and the set B. So G is the set of all the girls in the class, and M, sorry, it's not B, it should be M. So M is the set of all the, or this should have been B, I guess. So this is a set of all the boys in the class. So these, in this case, you can say that a student in the class either belongs to B or they belong to G, or they either belong or they don't belong, right? So they either a member of the set or they are not a member of the set. So these type of sets are called the crisp sets. But we can have the fuzzy set. For example, suppose we say set of all tall people. Okay, so we can say a person who's say 6 feet, we can say belongs to the set with membership 1, and a person who's say 5'9" may belong to the set with membership like 0.7 or something, and a person who's 5 feet may belong to the set with the membership value of 0. Okay, or in other words, doesn't belong to the set. So you have actually a membership value which is a value between 0 and 1, and every element in the set is associated with the membership value. Okay, so here this gives you your membership function for short, medium and tall. So this height is in centimeters, and we say that a person up to 150 centimeters has a membership value of 1 to the set of short people, and from there till 180 centimeters it sort of keeps decreasing, right? And at 180 centimeters you can say that the membership value of a person who is 180 centimeters is 0 or above is 0. Similarly, for medium, it from 150 centimeters it keeps increasing, okay, till you reach 180 centimeters. At 180 centimeters, the person with 180 centimeters has a membership of 1 to that set, then it keeps decreasing. Similarly, tall. Okay. So, usually if you take categorical things like short, medium, tall, etc., you find that using membership functions actually help in such cases. Okay, so let us look at what is a fuzzy set. Okay, so a fuzzy set A um, in the universe of discourse U. Okay, so that is something like the universe or the yeah. So if you take the universe of discourse U, in that if you have one fuzzy set A, it's such that if you consider values of x which belong to U, it is associated with one membership function mu A of x, okay, which gives the degree to which x belongs to A, okay, and mu Ax is got a range from 0 to 1, okay. So mu Ax belongs to the range 0 to 1, and one way of representing it, there are others also, but one way which is very popularly used is like this. So you say A is equal to, you have all the elements x1, x2, x3 and you have the membership values. So membership value by x1 plus membership value of x2, etc. Okay, so this is how you represent that. If it's continuous, you can represent it in this way. Okay. Now, if you consider two fuzzy sets, okay, so the fuzzy set is basically represented like this. So, if we have a set A which is fuzzy, it's usually represented like this, but you will find that in my slides, it's all just represented as A, okay, just to reduce on the complexity of producing the slides, right. So, if we consider two fuzzy sets A and B, okay, if you take any element x, the membership value of that element has to be the same in fuzzy set A and fuzzy set B. If that is the case, then you say fuzzy sets A and B are equal to each other. And you say that a fuzzy set is empty if all the values have membership function of 0, right. And a fuzzy set is called a universal fuzzy set or a whole fuzzy set if the value of the membership function is 1 for all the members that you are considering. So obviously some operators will be there, right. So if you consider say two sets A and B, right, and you want to combine those sets together. So how would you combine? You would use things like union, intersection, complement, etc., right. So if we have if you want to have A union B, okay, so that is what you need to do is that for every element x you have to take the maximum of the membership function of x in A and B, right. It is also indicated by this OR symbol, okay, which is the max operator basically. Similarly, intersection, you take the minimum of the two values, right, and the complement is when you take 1 minus the membership value. Okay, so if you take the fuzzy set A, then the fuzzy set A bar, okay, will have membership value of 1 minus mu A of x. So this shows your union, this is the intersection, and if this is your A, then this is your complement of that. Okay, so that is at every point the membership value will be 1 minus the membership value, which is there over here. And you also have what is called the algebraic sum, the algebraic product. Okay, so we have algebraic sum, algebraic product of the membership values. This is called a bounded sum because it doesn't go, I mean the highest you can have is 1, and you have a bounded difference where the minimum you have is 0. It doesn't go below 0 basically. And then just like you have in the crisp sets, even in the case of fuzzy sets, you have all these properties which are working. Commutativity, so A union B is B union A. Associativity, A union B union C. Distributivity, idempotency, so A union A is A. Identity, involution, so you take a double negative, you will get A. Transitivity, and De Morgan's theorem. So all these things work even in the case of fuzzy sets basically. Okay, so I have just taken one example over here. I hope it is clear. So suppose we have two fuzzy sets, okay, B1 and B2. So the top gives you the membership value, okay, of these value of these x, right, or the elements which are there. So it's asking you to find B1 union B2. So when you take union of two values, you have to take the maximum of the membership function. So this it will have 0, 1.52, 2.53 at the bottom, but on the top it will take the maximum of these two, okay, maximum of 0.75 and 0.6, which is 0.75, and it will take maximum of 0.3 and 0.2, which is 0.3, etc. If you take intersection, it takes the minimum, and B1 bar will be 1 minus the membership function in that case, etc. And B1 union B2 we have already done. So B1 union B2 bar on the top will be B1 union B2 1 minus the membership function of these, etc. So these are, all these values can be easily calculated. Okay, next we'll come to the fuzzy relations. Okay, so the fuzzy relations are just like the relations in the crisp sets, right? So you have one universe X and you have the other universe Y, and you talk about the Cartesian product between the two universes. So something like X cross Y. So a relationship RXY between X and Y, okay, is will actually be a subset of that cross product between X and Y. Okay, so if you have X and Y where X is not equal to Y, you get what is called the bipartite graph, and if X is equal to Y, then you get a directed graph. Okay, so suppose we have X as x1, x2 up to xn, and Y is y1, y2 up to yn. Then your fuzzy relationship Rxy will take all these in pairs, right? And you get the membership value here. So it will be the membership value of x1 and y1, x1 and y2, x1 and ym, etc. So this is for a relation which you call as Rxy. And here also you have things like union, intersection, etc. So if we consider two sets R and S, okay, so R union S of xy, so you are considering two relations. So this would be the maximum of mu R xy and mu S xy. intersectional will be minimum, then the complement, containment. So R is a subset of S only if the membership function of R using R is less than the membership function for S. Then you get the inverse, etc. Right? And the projection. For a fuzzy relation Rxy, R projection Y denotes the projection of R onto Y. So it is a fuzzy relation whose membership function is defined by max of, for all the x, if you take the max of that, right. So that gives you the projection of R on Y basically. So when you come to this fuzzy sets, you find that you have the law, what is called the law of excluded middle, okay, which is not satisfied. So if you take crisp sets, okay, if you take a set A, okay, and you say A union A bar, okay, you will find that it gives you the whole set, right. And if you take R intersection R bar, you will find that it will be the null set, but that is not the case for fuzzy sets. So you find that these two are not satisfied in the case of fuzzy sets and fuzzy relationships both, right. So this is what is different from the basic crisp set which we are talking about. Then we come to what is called the fuzzy composition. So fuzzy composition is ways in which you combine your x and y. Okay, so A is a fuzzy set on universe x and B is a fuzzy set on universe y. So the Cartesian product will be A cross B basically, okay, and your relation R will be a subset of x cross y basically, okay. So the membership function of the fuzzy relationship is given by of A cross B x y, right. It will be minimum of mu A of x and mu B of x, okay. You can have other types, for example max min composition. So max min composition is if you take two relationship R x y and S y z, okay, so you are taking x y and y z, so you denote it by R x y composition S y z, okay. So that will be min of all these values for different values of y and then the max of that basically. You can also have the min max composition, so you have min of max of these values basically. You can also have the max product where you have the product of these two. So all these are various ways in which the composition can be carried out between two two fuzzy sets, okay, or two relations Rxy and Syz, okay. In what ways can they be actually combined? Then we come to what is called the equivalence relation. So we talk about equivalence relationship in crisp sets, right. So in the crisp set, when we say that a relationship is equivalent, what does it mean? Okay, it means that it follows reflexivity, symmetry and transitivity, all the three properties. If it follows all these three properties, then you say that the relationship is equivalent, okay. It's an equivalence relationship basically. So in the case of fuzzy sets, let us see how the three properties are slightly changed. So if we take reflexivity, mu r xi should be equal to 1 for all x. Okay, so any element x which belongs, okay, to the relationship should be such that mu r, the xi and xi, okay, should be equal to 1. If this is not true, then you say that it is irreflexive basically. Then symmetry, okay, you have xi and xj. If you take all pairs xi xj, if mu r xi xj is equal to mu r xj xi, okay, then you say that it is symmetric. And if this is not satisfied, you say it is asymmetric basically. Then we come to the transitivity. So transitivity is like the membership function between a pair xi xj, and if you take xj and some other xk, right. So if this value is lambda 1 and this value is lambda 2, okay, then suppose you have a membership value between xi and xk. So you are taking between xi and xk and it's equal to lambda. So lambda has to be the minimum of lambda 1 and lambda 2. Okay. If that is the case, then you say that the transitivity is satisfied. Okay. It can also be represented in this way. Mu r xi xj it should be min of max of this value, okay, where all xi and xk belong to x squared or x cross x. So this is called max min transitivity because you are using max min over here. And if it is not satisfied for some member of x, then you say the relationship is non-transitive. If the given transitivity inequality for all members, okay, it doesn't follow, then you say that it is a anti-transitive. Okay, so these are some things. So fuzzy equivalence relationship has to follow all these three properties. If it follows all these three properties, then you say it's a fuzzy equivalent relationship basically. Okay, so here are one or two problems which I have just put down. Okay, so so the book from which this material is taken is called Soft Computing by Sadanand and Deepa. Okay, so that is the book from which this has been taken. So suppose you have two fuzzy sets like this, right? Perform the Cartesian product over these given subsets. Okay. In other words, what we want is we want a relationship A cross B, right? So A cross B will be in this way, right? So you are going to take 2 by 3 because this is 2 by 3. Okay. So if you have mu r x1 y1 will be minimum of mu a of x1 and mu b of y1, right. So you take the appropriate values there and put it into the relationship. So this is how you form this relationship, okay, and mu r of x1 y2 will be minimum of mu a x1 and mu b y2, okay. So that gives you the next value, that is 0.3 etc. Okay. So you can obtain this thing. Now here is another example. You have two fuzzy relationships, R is equal to this one and S is equal to this one. So this is on X and Y and S is on Y and Z. Okay. And you are asked to do max min composition, max product composition, max min composition. So R composition X. Okay, so how do you get these values? So here you have to use the equations we just went through, right, for composition. So suppose I want between x1 and z1. So what happens is, since R is between x and y and S is between y and z, your R composition S will be between x and z basically. So what would be x1 z1? So x1 z1 will be, you take max of x1 y1 for different values of y, right, and x1 y2 and you take the minimum of those, right, and you take the minimum of this and the minimum of this and you take the maximum of that. So this is the value that you are going to get. So in this way you can go through the entire thing and form this max min composition. Similarly you can do the max product composition, right. Uh, so you take T is equal to R dot S to get the max product composition. So you use whatever values we have for that, right. So max product, this is what you have to use, etc. Next thing that we study is what is called the membership function. Okay, so if we take a set of values, okay, so for example, if we consider the universe of discourse X, okay, so you will have a number of elements in that universe of discourse, say x1, x2, x3, x4, etc. So each of these values will have a membership value. Okay, so if you take these membership values and you put these elements together with their membership values, you get what is called the membership function. Okay, so it's creates the membership space. Okay, so it's possible in some cases that it could be just discrete, right. So you could have something like you may have x1, x2, x3, etc. and you may find that this has some membership value, this has another membership value. So your y-axis gives you the membership value which is between 0 and 1, say, right. x3 has some value, etc., right. So it could be discrete in this way, but you could also have a continuous mapping which takes place. Okay, so you can have something like, if you have x1, x2, x3, etc., and you have the membership value here, you may find that it goes like this, or it could go like this, or you could get membership value which is like this, etc. Okay, so you can get a membership function. So it maps X to what is called the membership space. Okay, so what you have is that the membership value maps X to the space, membership space M, which is between the interval 0 and 1. So here we can see membership a function, and we can see it has certain attributes, right. So what we will do is we need to go through all the attributes that are available. So we'll continue this attributes and see what are all the attributes in the next session.